So it is my pleasure now to serve as a moderator for a panel discussion that we put together in honor of Honorary Chairman Inaba's presence here and his awarding of the Berkeley citation. We are recognizing today Dr. Seiyama Inaba's extraordinary achievements as the world leader in robotics and automation. If you think about other people who had this impact, you think of names like Gene Merchant and F.W. Taylor, and he certainly is of that significance in what his company and his vision have created. And we're really pleased to have this opportunity to have this performance today by our panel discussion and have this presentation. I will be asking each panelist to comment on innovations in advanced manufacturing, robotics, and automation, reflecting their personal experience and expertise. Let me start with a brief introduction, starting on my right. On your right, my left, Al Pisano, who is the Fanuc Professor of Mechanical Systems, and many of you, everybody knows Al. Professor Paul Wright, the Berlin Professor of Mechanical Engineering and Director of CITRIS in the Banatao Institute at CITRIS, Berkeley next.
Good afternoon, everyone.
Arias, Associate Professor of Electrical Engineering and Computer Sciences.
Hello.
Associate Dean Masayoshi Tomizuka, who is the Neerhout Distinguished Professor of Engineering and longtime collaborator with Dr. Inaba and Fanuc. Dr. Kiyonori Inaba, who represents the Fanuc Corporation and also, for some of you who may know, was a PhD student of Dr. Tomizuka's. And Mr. Yufeng Wu, who represents the Fanuc Corporation. I'm going to start with Professor Pisano, and we have short presentations by each of our panelists, and if time allows, and that's partly my job, we will have a few minutes for questions at the end of the panel discussion. Al has always been in the front runner in the area of micro-electromechanical systems, so-called MEMS, and their applications. And Al, I'd like to hear from you about the roles of MEMS technology in advanced manufacturing.
Okay, thanks, Dave. I really appreciate it. And Dr. Inaba, congratulations again, and I'm honored to make this short presentation. So let's click through. All right, so what I'd like to do is go immediately to this slide, and I'd like to paint a mental picture for you. You are all familiar with the world of sensors. You all have a cell phone. Most of those cell phones have all kinds of sensors in them. At the very least, something that will sense up, down, left, right, so the orientation of the phone is known. Imagine a new world in which the sensors are able to survive environments of 600 degrees C, shock of 50,000 Gs, chemical attack, extremely high pressures. This world is coming. We are doing research in this sensor area, and these are the typical areas that you might see these sensors appearing first. Geothermal energy, oil and gas, gas turbines, aircraft engines, automobile engines. But of course, there are two sides to this sensor revolution. First, the sensors will go to places that we not normally put sensors, such as these locations. And second, these sensors will not only enhance manufacturing, but they actually will be part of the manufacturing process. So let me wrap up my short comments by leaving you with this thought. Imagine a world in which the manufacturing plants have automatically installed, not on the surface, but inside the components used to make a car. No more external wiring, no more wiring harness, RF communications among all the sensors. And these sensors go in places where we have never gathered information before, such as inside the combustion chamber, so that you can monitor the efficiency of the combustion spark by spark, event by event. Imagine a world made so much more efficient and so much cleaner by the combination of advanced sensor technology and new advanced manufacturing techniques. And with that visionary thought, or perhaps you might agree it's a visionary thought, I'll conclude my comments. Thank you very, very much.
Thank you, Al. I thought when you said you all have cell phones, you were going to say, and I hope you've got them turned off. Our second
Right,
panelist
to
is
get
my
to
good
yours.
friend, Professor Paul Wright. Paul has
Keep
worked
going,
on the traditional subject of metal cutting, as I have in his early careers, pioneered in the introduction of information technology, IT, to machining and manufacturing, and currently serves as the director of CITRIS, the Center for Information Technology in the Interest of Society. Paul, from your point of view, what is the most exciting aspect of IT, in particular IT as related to manufacturing and automation?
Dave, thank you. Let me also wish my warm welcome to Dr. Inaba. Thank you for joining us today, and the provost, Professor Breslauer, and all of my colleagues. I think all of us know from the recent political environment that manufacturing is now very much back in the public eye, advanced manufacturing, and that is already, with the right investments, has created a new rebirth of sophisticated advanced manufacturing, especially in the auto industry. And as a result of the work that the Obama government has done in what were called the bailouts of the auto industry, but in fact we're allowing enormous reinvestments into automation and IT, as Professor Dornfeld hinted. That's been a very critical element in the last few years of regenerating the U.S. automobile industry, many of which use GM Fanuc controllers for their work. And as a result of that, our investments in information technology have saved 1 million jobs in the automobile industry. And according to the statistics, they have also created 250,000 additional jobs in the automobile industry because of investments in information technology. And just to be a little humorous, I only wish I had an accent from Arkansas instead of my British accent, where I could imitate President Clinton by saying something like, because of those investments, President Obama, 250,000 new jobs, Governor Romney, 0, or whatever he said that night. So forgive my informal attempt to be an Arkansas governor, hoping who will not be our next president. So I'm showing my political leanings right here. So 20 years ago when I joined Berkeley, many of my colleagues in this room, I'm looking out, Professor Goldberg, Professor Horowitz, many distinguished colleagues in this room, and Professor Dornfeld and I, we began a project called CyberCut, and that's shown in this slide here, where our vision was that many of you who are brilliant designers sitting on the top left there would connect with early prototyping methods such as fused deposition modeling and stereolithography in order to create an initial item that we can actually make now in Echeverry Hall or in Sitaja Dye Hall, and that's being done at the bottom there. But what's key for automation, what's key for the automobile industry is to be able to scale that up using information technology in order to make products by the many millions, so that when you go to Target and you buy those plastic products that you and your family use at the weekends, those are made all over the world, especially in America and especially in Japan, especially in Europe. That's being done with information technology because of the links from designers like yourselves to these very high volume manufacturing activities. So information technology around the world, connecting ideation, done famously by Apple, connected to rapid prototyping, done by many of you students in the room, connected to large-scale automation. Those are key links in the IT cycle. And those design rules have been developed at Berkeley. They've been developed by our previous dean, Richard Newton, and Alberto San Giovanni Vincentelli in EECS. And those same design rules are being used by mechanical engineers for this industry. And as we go forward, they could be used by biomedical and biotech engineers to create those design rules. So it's been a very key part of our work. And just in my last slide, I'll just show that what we're also doing to move that work forward is to make combined mechanical and electronics work here. What you see in this particular slide is an additive manufacturing process that we're developing. The work is in Hearst Mining at the present time in room 130, and that's making new products, again, using these design rules that combine energy scavenging, energy storage, microelectronics, wireless systems, And that's the sort of next generation cell phone that Professor Dornfeld mentioned that would combine sensing, energy storage, and be the next generation of new products. Again, these will be made using information technology to scale up to the very large volumes that we need, again, to make all those manufacturing jobs happen. So I'm honored to be able to give these small introductory remarks. And now I think I'll hand back to our distinguished chairman. We've been good friends now for 35 years when we started our career in manufacturing together. So it's an honor for me to be here with Dave today. Thank you.
Thank you, Paul. I have to say that of all Paul's unique characteristics and the differences between himself and an Arkansas governor, the accent was not the major distinguishing characteristic. Our next panelist is Professor Ana Arias from EECS. Ana's research is in the area of physical electronics. Her interests are in electronic materials for flexible sensors, fully printed, and correlation of materials deposition conditions and morphology on device performance. Anna, I wonder whether you can share with us your thought on manufacturing in physical electronics, in particular with respect to domestic capability versus worldwide capability.
Sure. Dr. Inaba, it's an honor to be here in this panel. The area of manufacturing and electronics or physical electronics that I work on is printed and flexible electronics. This area has got several people interested in because there are several motivating factors that brings different technologies and different materials into electronic devices. It has a little bit overlap with what Paul just said about additive manufacturing. And by that it means that instead of using the techniques that are used in conventional silicon technology, you now use materials that are processed from a solution or from melt. And because they are in a different form than silicon, you can deposit them with different machinery. And in this case, we use printers. And the idea is that you could print electronics and sensors in the same way that you would print a document. So that has several advantages because you can make the turnaround much faster than silicon gives you. It is more environmentally friendly because you don't have waste of materials. You only add the material where the functionality of that material is needed. And that can be a semiconductor or a dielectric or a conductor. The other advantage of this technology and what has many people interested in is that you can then integrate sensors and electronics with the same fabrication process, which again makes manufacturing more efficient. While silicon, you have a process for MEMS that is completely different than a process for CMOS. The main idea or the holy grail of this area is that you will go from an area where you have subtractive manufacturing, where it has many steps in order to get one feature, one electronic feature in a substrate, to a place where you have one step deposition and patterning, which is the additive manufacturing or additive printing. Here we have several people several groups working towards flexible electronics. And this involves different materials, as these materials are in form of nanowires or solutions, nanoparticles, so there's a lot of nanotechnology. The applications that we are looking at can go from artificial skin, where you have sensors and electronics integrated to mimic touch. We also have, we are working on hardware for MRI to make not only the experience of having an MRI scan better, but also the image quality. Wearable medical devices that could monitor vital signs and how healthy you are. Also, we have a project together with the Berkeley Wireless Research Center to start embedding electronics in the wall. So we call it electronic wallpaper, where you start interactions with displays and sensors that are placed in the wall. And of course, this all depends on a very efficient manufacturing. So row-to-row processing would be one area that we are interested in. So just to finish, to compare U.S. versus the rest of the world, in Asia, there are many manufacturers of displays that are interested in this technology. In Europe, there was a lot of investment from different governments, and I think the biggest investment was from Philips and the Dutch government that formed what's called the HOST Center, which is a research center dedicated for lighting and photovoltaics done in rows. They also have a partnership with IMEC in Belgium to do flexible devices more in the medical device area. In the US, things are more scattered. There are several groups at universities that work on flexible electronics. There are several startup companies, but it's not as focused as in Europe, I would say.
Great. Thank you. Let me call on Professor Tomizuka, Masayoshi Tomizuka next. We go by the name of Tommy, and as with Paul and myself, we go back many, many years. I think I came just a couple of years to the campus after Tommy arrived from MIT. He's worked on the control of mechanical systems and mechatronics during his career, and one of the leaders in that tech area. Tommy, I'd like to ask you what mechatronics means to you, in particular mechatronics as related to robotics and automation.
Okay, thank you, Dave, and good afternoon. So, Dr. Honorary Chairman Inaba, thank you for your visit, and thank you for your long support, and also congratulations on the Chancellor's Award. So, my title is Control of Mechanical Systems, Mechatronics Approach. And I've been teaching control and doing research almost 40 years. And at the top of this slide, what I have is a typical block diagram I've taken from any undergraduate or graduate control textbook. And if we look at this diagram, and also the way we teach control, we normally get the impression that normally the controlled plant or target system, I call here, is given, and actuator instrument sensors have been already selected. And given those, control engineer is asked to design control. What should be the control algorithm? Okay, so that's normally what we get impression. But the controller design or control algorithm design is a very important part. But ideally, we would like to design controller and controlled plant, maybe co-design those two. And in fact, one of the Master of Engineering capstone project, we are looking into co-design of the target system and controller from the viewpoint of robotics. That's new Master of Engineering program. And also, our thought goes to what kind of sensors should be selected, what we should measure, and where we should be placing sensors. And so is actuators. What should be the power source, what type of actuator we should be using, its size, and so forth. And then we synthesize, integrate all of those elements to achieve the control objective in the best achievable way. And in doing so, we often look for synergy. Okay, synergy means that 1 + 1 should be greater than 2, and we should accomplish something we will not be accomplishing just by looking into the controller. And this holistic approach is what I call mechatronic approach to the design of control systems. My laboratory is the Mechanical Systems Control Laboratory, and we work on a variety of mechanical systems, and we have quite a few mechanical hardwares, some of them too big to fit in the laboratory, but our students have opportunity to work on those mechanical hardware or mechanical systems. Now, given any mechanical system, whether it be robot or vehicle and so forth, as a university laboratory, we are not interested in just finding an arbitrary solution. We would like to find a solution strongly supported by scientific basis. But at the same time, we would like to see that our work does not remain as an academic exercise in a university laboratory. We would like to see our result really applied, help solving the real-world problem, either maybe immediate future, if not in distant future. We would like to see those solutions be applied. So my students work on mechatronics research by developing and applying control theories, hardware, implementation skills that they learn from the coursework or maybe in the laboratory. And typical projects include analysis, simulation, construction of experimental systems, and implementation and verification working on the experimental system. In the area of robotics, my student and I have been extremely fortunate to work with industry partners. In particular, I have had long association with Fanuc, and we benefited a lot learning the problem, issues associated with the robot on the factory floor from Fanuc engineers. And they also provided robot to our laboratory, and we can really learn something we will never learn just working on simulation model only. So today, the next panelist is Dr. Kiyonori Inaba, who works now at the robot, and also he's a graduate of my laboratory. And I'm very pleased to touch my button to you. Okay.
So thank you, Tommy. Actually, before I introduce our two colleagues from Fanuc who will present one after the other, I just have to say that the first robot on campus was a Fanuc robot. Probably the early 80s, it was a cylindrical coordinate machine. We did not focus on manufacturing automation. We did a demonstration for Cal Day in which it opened a beer bottle and poured beer into a cup without having a head that went over the plastic. It was pretty impressive. Which, actually, that might have led to the decline of U.S. productivity right there. I'm not sure. So we have two colleagues from Fanuc who are going to present one following the other. Dr. Kiyonori Inaba, as Tommy introduced, and Mr. Yunfen Wu. Kiyonori obtained his PhD degree working on learning control as a student with Tommy at Berkeley. Mr. Yunfen Wu was with the Robot Research Laboratory at Fanuc. So first I have a question, and actually, Mr. Wu, you can stay seated for a second. You can sit down, and you can follow Dr. Inaba. I have a question for both of you to think about and then answer in tag team fashion. It's interesting that a PhD study directly helped and contributed to your industrial job, especially working for your grandfather. Can you and your colleagues share with us what you've accomplished with respect to learning control and applied to practical machine design and utilization for robotics? And then you can now, you're going to use the...
Okay, so most different thing is the limitation of hardware. So learning control use lots of power computation. So that's why we need to modify the calculation algorithm. That's the most important thing when we establish the product. So thank you very much, Professor. So I'm really happy to make a presentation here about learning control. So the relationship between Berkeley and Fanuc started from Professor Kobayashi and is more than 25 years. At that time, the relationship, such an international cooperation was unusual. However, both Fanuc and Berkeley had good mutual communication. Currently, Fanuc has branches in all over the world. There are so many foreign employees working in the headquarters in Japan. Dr. Wu, next to me, is also from China. Over the year, Fanuc, the relationship has become stronger. Right now, we have cooperated in the field of robotics. One of our challenge is to achieve high-speed motion. High-speed motion has various factors which become the cause of robot vibration. For example, the deflection, compression, tension of the arm can increase. Also, the transmission error backlash, elastic deformation, and friction of reducer can be the cause of vibration. The solution for this was just to slow the motion down. However, these vibration issues can be overcome by the learning control, which was studied at UC Berkeley. It realizes smooth high-speed motion without vibration. The learning robot comes from this technology. It introduces learning control and sensor technology and overcome the vibration issues of high-speed motion, which has not been utilized before. It results in high cycle time reduction. Please see the effect of this function. The upper video, the video on the top shows the high-speed motion without learning control. The video on the bottom shows high-speed motion with learning control. As you can see, the vibration can be suppressed on the robot with learning control. Utilizing this technology in real application, the motion speed can be sped up. To summarize the future, this function realizes smooth high-speed motion, and it doesn't require special instruments. Any mechanical change is not required. It doesn't require special skills. Anybody can use this function easily, and the same performance can be accomplished by everybody. This function contributes the improvement of production efficiency, for example, in reduced cycle time on bottleneck processes, and also can be used for handling of heavy objects. Handling heavy parts with large offsets might be one of examples. Recently, many automobile companies started applying this function to their factory. We are looking forward to the future of this function. Thank you.
Dr. Wu, you want to continue? Thank you.
Good afternoon, ladies, gentlemen, and professors. It's my great honor to visit UC Berkeley. Next, I will talk about another typical robot we named Genkotsu robot from Fanuc. Genkotsu robot is a lightweight and compact assembling robot. Based on the high-speed characteristics of parallel link mechanism, Fanuc added texturous motions by 6-axis unique wrist mechanism. Therefore, Genkotsu robot contribute to handling and assembling of small parts. For an example, I would like to show you a video of colored sorting of pills. This video shows the colored pills. We sort the pills very quickly, depend on the colors of pills, with the high-speed motion of parallel link mechanism. And then also we scattered the pills to the plate using the unique 6-axis mechanism of the robot. For further improvement of production efficiency, speed up of Genkotsu robot was needed, and the learning control is one of the solutions for the speeding up for Genkotsu robot. Therefore, UC Berkeley and Fanuc is cooperating on Genkotsu robot speed up for the enhancement of automatic assembly operation. Thank you very much for your attention.
Thank you, Dr. Inaba and Dr. Yunfen. Amazing research. Actually, Professor Pisano was telling me before that he saw this pill sorting robot working in Fanuc in Japan, and it was amazing the speed with which it was able to sort some of these things. So thanks to very careful time control, I'd like to take credit for that, although I think the panelists did a great job. We have time for a few questions, and if I might, maybe I'll ask the first question. I'd like to ask it to our two colleagues from Fanuc. In your, so Dr. Inaba, Yunfen, in your presentations, you emphasized the speed and productivity improvements, but I understand also that a real example of the benefits of automation is quality control. And I'm wondering if you could just comment on, from your point of view and the eyes of the user, if it's the productivity or the quality or the both, or both of them, that actually makes kind of the major impact of the application of robotics to manufacturing.
Actually, the Fanuc robot motion controller of the Fanuc robot are tuned for common systems, and therefore there are one problem that is the motion controller is not be optimized for some individual systems. So by introducing learning control, we can make the optimized motion controller for our Genkotsu robot.
Very good. Dr. Inaba, do you want to add anything to that?
So optimization is kind of important topic for us. So usually we need to be in the safer side. So that's why tuning is really conservative. So by introducing learning control, the high-speed motion, as Dr. Wu said, so will be accomplished based on system by system. So
good. Great.
That's
Thank
our
you.
purpose.
Thank you. And now we have some, or a microphone, two microphones, if there's some questions for the panelists primarily. I don't take questions.
Thank you. Thank Thank you for the wonderful presentation, Arnav and ER at the Fanuc too. A quick question, it might be a high-level question for the Fanuc gentleman. And the recent PCAST report to President Obama about advanced manufacturing, it talks about a term called as value of death. And the value of death is in manufacturing innovation, where the research from industries, research at labs and universities has not been able to, or some of the times not been able to brought to industry production and innovation. So how can the participation from industry engage or enable some of more of this innovation to come to production and automation? And you talked about some of the really good products, what you're talking about. Thank you.
Yes. As I said before the presentation, we had kind of really difficulty in installing the algorithm. So in the academic area, most important thing is maybe theory, so to achieve the goal. However, so in installation of academic new theory, we need to think about more cost, so like customer demand. So that's the totally different point in my understanding between academic area and real product area. So both would be a little bit different, but we need to cooperate it with each other for developing new product.
Good, thank you. Another question.
Who had a question? Oh, you did. Stand, please. Hi, I actually had the chance to intern at Shanghai Fanuc over the summer, so here I have a question for Dr. Inaba, or we call her Inaba-sensei. And actually, for the LVC, my colleagues over there were trying to promote it to different clients over in Shanghai. And what we see as a problem is that it takes a long time to help the robot learn every point of the welding process, so it makes the process faster. But if we change a point, it takes an effort we need to relearn the point, and then it can do the process again. So every time there's a change in the factory, we need a specialist from Fanuc to come in and actually help the robot relearn the process. So I'm just wondering how you see as the connection or conflict between the practicality and the research and the effort that went into this.
Oh, that's really technical question. So it seems you are really familiar with learning robot. So as you pointed out, most difficult things for learning, it's based on the trajectory. If the customer changes the path, so in that case, sometimes relearn is necessary. It takes a little bit time to do it. So right now, we are doing learning. So based on the trajectory, however, for the future, in my understanding, what I'm going to do is that doing a sample motion before learning and generate some learning data, which is used for general motion. That's my final goal. So in that case, we don't need relearn anymore. Thank you.
So I think we have time for one more question, and then I have to turn it over to my boss.
My name is Sang Gi-min from Berkeley National Laboratory. I'm currently working for the corresponding to U.S. manufacturing initiatives. As you know, as he mentioned, that recent PCAST report said the U.S. manufacturing having a serious problem. So the U.S. government is launching multiple manufacturing initiatives and things like that. But one of the efforts is to try to reshore the manufacturing. So we built the products inside of the United States. The biggest challenge to do that is automation, because you cannot simply compete with Chinese labor and infrastructure, low cost, and things like that. So today I see like two key elements here: the Genkochi robot and the learning robot is going to be very key component to achieve this automation. Especially the complex assembly work is really required to assembly robots and stuff like that. But none of the current robot is capable of replacing this labor. So do you have any plan to replacing or advancing the robot assembly technology?
You could just say, you could just say yes.
Okay. So, personal opinion. So, assemble is kind of final goal of FA automation in my understanding. So right now we are going to introduce it. As you know, Fanuc is really famous for vision sensor intelligent system. We introduced accelerometer for a learning robot. It's kind of intelligent system. So for doing a human, so we need intelligent, so which means that more sensor technology is important. So that's my opinion. Thank you.
And also for automated assembling process, because there are originally there are so many peoples, and the space is very narrow. So if we provide some robot, something like Genko's robot, this can just replacement by human. That is one method. And we can put a lot of robots very narrow, in narrow space, and each robot do their work. And
Very
we
good.
can just make the production line, just like we use human workers.
Very good. Can we thank our panel? And I'll turn it over to my boss, Dean Schatzky.
Thank you all very much for that fascinating discussion. Before we close, I'd like to add a very special thank you to our outstanding friend, Dr. Inaba. You know, Provost Breslauer said this, but I'd like to say, as a robotics researcher, you know, it is a point of really very, very special pride to see Fanuc in the stratospheric heights, the first robotics company to be in the stratospheric heights of the top companies in the Nikkei. You know, it is really amazing to see the heights to which Fanuc has climbed. You know, you've seen some of these robots, and as you look at your cell phones, it's not long before every one of them is going to be manufactured using those robots that you saw in action. And for a robotics company, and I know a lot of my colleagues here who've always waited for this day that we would say that robotics is, you know, one of the top companies. So we'd like to recognize you, Dr. Inaba, for being a master at advancing manufacturing and innovation over these many, many decades. So congratulations, and thank you very much for coming. I'd also like to thank our student co-sponsors, pioneers in engineering. And finally, we hope that all of you will join us in a reception right outside in the Kwame atrium. Thank you all very much for being with us, and go Bears.